Hello and welcome to my tutorial on creating a basic vision transformer that can categorize images. So, in this tutorial, we're going to be going through this. We're going to be first going through kind of like the theory of what a vision transformer is and how is it modified from like a regular transformer and whatnot. Then, what we're going to do is we're going to actually go ahead and build the vision transformer. So, let us begin. First, we have to understand what is the vision transformer, right? So this is the theory portion. So first I'm going to start with the transformer, right? It's transformers. So obviously, we need some transformer blocks, right? Attention into MLP. We need transformer blocks. That's necessary to how the transformer works, right? And then obviously, we're also going to need position and text embeddings. But this isn't a text transformer. This is a image transformer. So what we're going to do is we're going to have image patch embeddings, right? So these are just going to be convolutional layers, right? So it's a small CNN in there to just do patch embeddings. And we're also going to have position embeddings. And we're obviously going to have the output layer and just the regular transformer stuff. It's just, instead of having text embeddings, vision transformers, they have image embeddings. So just like with a regular transformer where you take text and then you feed it through a text embedding model, here we're taking image patches and feeding that through an image patch embedding model, and we're going to be using a CNN for this, right? It's just some convolutional layers. And so, what is an image patch? An image patch is just a small square of the image, right? So, I'm just going to use the example we're going to be using today. If you have, say, a 32 by 32 image, and then you have like a 4 by 4 patch in the image, what you have is the image is actually 8 by 8 patches, right? So now what you have is you have 64 image patches, and that's the input to the transformer. It's a 1D input to the transformer. And so this is just the general architecture of what we're building, right? It's you'd have your input image, and then you like patchify it, so you just cut it up. Then it goes to position and image, like embeddings, like patch embeddings. And then you just send it through a bunch of attention layers, and then you have the output layer, which is your classification, right? So we're just going to be rebuilding this effectively from the ground up. Now what we're going to do is we're going to actually set up our environment prior to actually making the model. So first, as you should always do, you should make a new virtual environment, right? We'll call it Vision Transformer. We're making a Vision Transformer. And then we're going to activate it, right? Wait, and activate. Cool. And then we're just going to install the stuff we need, right? So we're going to install Pytorch, right? And we're going to install Torch Vision, because that actually has the data set we need. And then we're going to install TQDM just to handle some of the training stuff, right? And so it's going to go and install. And while it's doing it, I'm just going to talk about how we're actually going to go and build a model. So first, we're going to build a model, and the model, I'm just going to go from the ground up, right? So we're going to start with patch embeddings, then we're going to do attention and MLP, and we're going to bring those together into the transformer block, and then from there, I'm going to go and I'm going to build the actual final model, right? So I'm just going to start from the most basic elements, and we're going to work our way up until we get to the entire model. And then for training, I'm just kind of going to go through a similar thing. So I'm just going to set up the data sets, the loss function, the optimizer, and whatnot, and then I'm going to make the train and test functions, and then I'm just going to have a training loop. And so there we have that. And what I'm going to do now is I'm going to create a new file. I'm going to create vision transformer. And this is just going to be the file that stores details about the model. And so obviously, because we're using Pytorch for this, what we're going to do is we're going to import Pytorch, and we're going to import data class as well, right? And so this is just going to be some helper stuff to help us actually build a model, because we're relying on Pytorch here. And so the first thing I want to do is actually create the config data class, right? So it's just one place that we can edit a bunch of the parameters for the model, right? So what this config data class is going to be is this config data class is going to effectively store everything we need. So it's going to have the image size that's going to be going into this model. It's going to have the patch size. It's going to have the number of input channels, so there's a number of colors in the image. It's going to have the number of output classes, because we're making a classification model. So what we're going to be doing here is this is the total number of possible output classes can be. We're going to have an embedding dimension. We're going to have, basically this just contains all the stuff we need for the actual transformer model, right? Now what we have to do is actually create patch embeddings, right? And so what I'm going to do here is I'm going to make a new class. It's just patch embed neural network dot module, right? So because this is just a small module in the neural network, and so we have to implement the init and the forward for this, so x, right? And we're also going to feed in config in here as well, right? So we're going to be implementing this, and so then now what we're going to be doing now, right? So what we're going to be doing now is we're going to be setting up all the stuff that the image patch embedder is going to be needing, right? So we're going to set the image size of the patch embedder to be the image size from the config. We're going to set the patch size to be equal to the patch size of the config, and we're also going to be setting up the number of patches that this embedding model is going to have to handle. We're going to be setting that as just the size of the image, right, divided by the size of the patch. And of course, because these are both 1D numbers, because that's just the width of the image and the patch itself, we're going to be squaring it because images are 2D. Then we're going to actually make the convolution layer here. This was just saying of variables. So now, proj, right, the convolutional layer, it's projecting the input patches into the embedding space. So it's proj, so projection, is neural network dot conv2d, right? We're doing a 2D convolution. Number of input channels, this is just config dot in trans, right? The number of input channels. Output channels is config dot embed dimension, right? So we're taking the number of input channels, which is 3, right? And we're just converting it to the embedding dimension, right? So each image patch will come out to the image dimension, and the kernel size, we're just going to set that to config dot patch size, right? So in essence, it's just going to be in patch size, and we're also going to set the stride, right? So equals config dot patch size. So what we're basically doing here is we're bringing the patching step into the patch embedder, right? So it's just a convolutional layer, and it's taking the full input image, and it's converting it down into, if we use these numbers, for example, an 8x8 end of a convolutional layer, right? And so we're effectively using this as the patching as well as the convolutional layer in the patch embedder. Now we actually have to do it forward, right? So when we actually run through the embedding model, what does it actually do? First, x equals self.proj, right? We're running it through the convolution. Then we're just going to change the dimension of this, right? Because right now it's a 2-dimensional thing. We need to change it to a 1-dimensional thing, right? So x equals x dot flatten 2, right? Because we're flattening it down. And then we're just going to transpose it 1, 2. And what this is just basically saying is instead of it being in 1 dimension, we're going to set it to be the other dimension. We're just going to transpose the model. And so now we effectively have like a horizontal list of image patches that have also been embedded into the latent space of the model. And obviously we're going to return x. Right, so this is a patch embedder, right? So not only does it do patching, this one also is embedding. We've done it as one module. Now what I'm going to do is I'm going to actually do the attention layer, right? So this isn't the full transformer block, because I'm going to do the MLP after that. That's a little bit more simple. But we're just going to do an attention layer, right? Neural network dot module. So again, we need init, which with self and config, and we also need the forward with self and x, right? And so when we're initializing the attention block, what we're going to be doing is, obviously, we're doing the neural network module initialization. Then we're just going to do a whole bunch of the like variable bring in, right? Like the number of heads is config dot heads. I'm just going to do more of this like variable bringing in, right? And then next we're going to find the dimension of each head, right? Because then this allows us to do some stuff with the attention layer, right? Because, you know, we're scaling it up and doing attention and whatnot. And so, right, so we have the embed dimension divided by the number of heads, right? So this is the amount of each embedding that each head will do, if you want to think of it like that. And then we're going to set the scale, and that's just the square root of the given head dimension, right? Next, we're going to actually like set up the actual attention part of the attention layer, right? So we're going to set up the key, query, and value, and that's just a linear layer, right? The in features is going to be the embed dimension, right? Because we're bringing in the embed dimension, and for output, we're just going to be doing the embed dimension, and we're going to be multiplying that by 3, right? Because you have your embedding, and then you have to generate a key, query, and value of equal size. And so we're multiplying it by 3, and then we're just going to be cutting it into like 3 halves. And then we're also going to be setting the bias of this to be config dot qkv underscore bias, right? Next, we're just going to set up the attention drop and then the projection. So first, let's set up the actual attention drop. So this is just a dropout, right? We're just having a dropout here, right? So self dot drop equals neural network dot dropout, and so we're just going to bring it in from the config, right? Config dot attention drop, right? Now you will notice that in this specific config it's 0, but if you're like scaling this up and whatnot, you will want to introduce a number here, right? And then now what we're going to do is we're going to have the actual projection layer here, right? So self dot proj equals neural network dot linear, and it's going to take the config dot embed dimension, and it's just going to keep it the same one, right? So this is, you can kind of think of this as cleaning up from the actual attention layer, right? The attention layer does stuff, and then we clean up from it, right? And then we also have the dropout from here, right? And then dropout config dot drop, right, and so this is kind of all we need. But now what we have to do is we have to do the actual like computation of attention, and this is a little bit more complex, but you know, we can bring it in, right? So b comma n shape, and then this is just the actual shape of the stuff being fed in, right? B is the batch size, n is number, right? Like you get that, right? Then qkv equals self dot qkv of x, right? Because we've set up the actual layer here. It's a linear layer to generate qkvs, and then we're just going to reshape it, right, so that it can better match the stuff. So we're going to reshape it into the batch size n, right, 3, because you know we have 3. It's the query key and value, so we have 3 there. We're we're going to set as number of heads divided. So then we're going to have the number of heads, right? So we're taking query key and value, and we're going to be dividing the work among however many heads we have. So in this case, 12 heads. So we're going to have the query key and value, and then it's just also going to have the number of heads. You can think of B and N as more like just parameters for like the actual training and whatnot, so you can kind of ignore those. But here we're just going to be effectively having like a 2D grid with the number of heads. And obviously, how much work is each head going to do is C divided by the number of heads, right? And we're just going to commute over these, and we're just going to go 2, 0, 3, 1, 4, and so this is just some numbers, right? Then we're going to actually get the query key and value, so Q, comma, K, comma, V equals Q, K, V of 0, comma, Q, K, V of 1, comma, Q, K, V of 2, right? We're just going to be pulling out the query key and value, and then the actual attention is, first we're going to be doing a matrix multiply with the queries and the keys, and obviously we have to transpose the keys because the keys are just a list of, are in like the same like vertical format. We have to like transpose it so it's horizontal, so you can actually multiply those matrices together. So we're going to transpose it. And we transpose it -2, comma, -1, and we're just going to multiply it by the scale, right? Because we're making the stuff bigger, we have to actually make it smaller so we can combine it all together again. Then we're just going to do softmax, right? And we're just going to set the dimension is -1. It's just straight up just a softmax, right? We're not going to touch the dimension. And then we're going to add the dropout, right? So it's going to be self dot drop and right. And so then we've done the calculus of attention. Now we're just going to have to clean it up with the projection linear layer, right? So X. Right, so we're going to do another like multiplication with the attention and the value itself, right? And so obviously, because these are going to be in the same size, we're now going to transpose these. So it's back to the original thing. And we're just going to bring the reshape back to B and C, which is, again, just like training parameters. You don't particularly need to worry about that. We're going to get that into that more detail a little bit later. And so X is self.proj. And we're just going to do the prediction and then the dropout, right? The dropout layer. And then we're just going to return X, right? So this is our attention block, effectively. We just go through, we compute the query key and value, then we like transpose them so we can actually like do matrix multiplication of them together, and then we do projection and then mirror out, right? Then we're going to do the MLP bit of the attention, and this is actually going to be very simple, right? We're just going to have linear layers and then activation functions and whatnot, right? So again, we're going to have the init with self and the config, and then we're going to have the forward, self and the actual input to it, right? So then, well, obviously, right, and so then, what parts are actually going to be in the MLP? We're going to have self. I'm going to call this linear 1, and that's network dot linear. The input is the embed dimensions, right? Because the attention will output stuff in the embed, and so this is just the standard size of stuff. And the output is the config dot embed dimension multiplied by config dot MLP ratio. And the multiplying by MLP ratio basically just gives us more neurons to do computation, right? Because This is going to take a lot less computation than the attention. What we're basically just saying here is just use up more computation, because we're already bottlenecked here, so might as well just put more computation into it. Right, and so obviously MLP ratio is a float from the thing, so I'm just going to convert it to an int. And so if you wanted like a 2.5 times MLP ratio, you could. You just need to like change it in the config. Then the activation function, I'm gonna call it AF. And so we're just gonna use galu, right? It works, don't need to touch it, it's galu. Then linear 2 is neural network dot linear. And so again, it's just, we're just going back down the like sizes, right? So we have the int of config dot embed dimension multiplied by config dot MLP ratio, and then the output size is just the embed dimension, right? And then obviously we have a dropout, right? So neural network dot dropout, and it is config dot drop rate, right? And so then when we're actually like calculating this, it becomes very simple, right? We basically just iterate through this, right? So first x is self dot L1 x, then x is self dot activation function of x, then x is, again, like you can kind of tell the pattern. We're just going through these. It's a very simple one, right? Self dot drop out of x, and then we're just going to return x, right? It's like the MLP, there's really not much that you can do here. I realize I should probably put another dropout again after the activation function, right? Because we have the two different linear layers. There should be a dropout, right? Now, since we have the MLP layer and the attention layer, we can just make the transformer block, right? And so this transformer block is what's actually going to be repeated like n times, or however many there is in the config, right? So it'd be depth, right? It'd be repeated depth number of times. So, and so obviously we have this self in the config, and then we also have the forward. Right, and so then again, just following the rules of Pytorch. So first we have to do the actual normalization. We're going to do a layer normalization, and it's just going to be the embed dimension. Just do the first normalization, then self dot attention, right? It's going to be our attention that we made earlier, and we're just going to feed it in config. Then we're going to do another normalization at the end. Right, this goes all the way back to the attention is all you need paper. This is just, we're doing all the normalizations. And then we're just going to do the MLP part of it, and it's just MLP class, and we feed it in a config. Then when we're actually running this, again, very simple, x equals x plus self dot attention, and then self dot norm 1 of x. Now, of course, remember, you kind of have to pay a little bit of attention to this, because this can cause a trip up. Make sure it's x equals x plus. Don't just do x plus equals, because that causes issues with Pytorch. And then not attention, MLP. We're going to do the MLP here, and we're just going to do norm 2, and then we're going to return x. And this is your attention block, right? So this is just like a regular attention block. Nothing too fancy here. And if you remember the vision transform paper, they basically did the same thing, right? The only fancy thing was having image patches instead of tokens, and we're basically just kind of doing the same thing. This is just like a bog standard transformer, right? Next, we're going to actually make the vision transformer, right? Neural network dot module. And so again, we need the self comma config, and we also need the forward, right? Self, comma, x. So then so I was thinking about too far ahead forward. We're going to do the super dot dunder init, right? And then we're basically just going to do the bringing of variables in, right? Self dot config because we're actually going to need a little bit more. Self dot patch embed equals. We're going to bring in a patch embedding because this happens at the start. We're going to feed it in our config. Then the number of patches is self dot patch embed dot number of patches. Right, we're going to pull it directly from here. We could just do config dot. Wait, I guess number. Hold on, did I put number of patches here? No, we didn't. Okay, so we do have to pull it from there. Self dot patch embed dot n patches. Then what we're going to do is we're going to actually set up the position embedding, right? So first we're going to set up just like a general like token, right? So this is from the original vision transformer paper. So basically what it is it's just a token that at the very start that, so you can kind of treat image patches as like a token, but this is just like another one that's not an image patch, and then the model can actually train the numbers that go into here. And then it does attention on it and whatnot. And so what we're going to look at the end is basically just going to look at the value from this as the final output, right? And so the reason we're doing this instead of just one of the tokens in the actual model is because this way what we have is just like global information effectively, because it's not tied to any specific locality. So because it doesn't have to store information about a specific locality of the image, we can kind of use this as like a pseudo global. And so that's what we're going to be doing here. It's just a token we at its start, and that's just, you know, a pseudo global. So this is just a parameter. So we're just going to start this out with like a bunch of zeros, right? And wow, Canadian spelling of zero in there, you know? So, you know, we're just going to, you know, just initialize it. Says the embedded dimension. Then we're going to actually do the position embedding, right? Self dot position embedding. And so this is another parameter that the model can tune and train on and whatnot. So torch dot zeros 1. And for the actual size of the thing, we're going to have number of patches plus 1, right? Because we have the number of patches that we're doing patch embedding for and whatnot, plus the class token, like the global, like the pseudo global token, effectively. So there you go. And obviously, you know, it's embed dimension, right? And then obviously we have dropout, right? The position embedding dropout. You'll know dot dropout. And so the actual rate of this is config dot config dot drop rate. Next, the actual blocks is it's going to be a module list, right? It's just a list of modules, right? That is going to iteratively run on. And we're just going to use list construction because we don't actually need to be fancy here. We're just going to make a block of config for, and we don't actually care about this variable, so I believe it's underscore in range, and then it's just going to be config dot depth, right? So this is just a number of blocks we have in a row. Then we're going to have the like ending norm and linear and whatnot. So norm, dot layer norm, config dot embed dimension, and then set the head to be dot linear, and the and so this is like the ending output head. That's like the final cleanup and whatnot. And so obviously inside we get the embed dimension, and then the final output. This is going to be our output layer. It's config dot classes, right? So this just takes the final thing, and then we're just gonna, just get the number of classes there, and so boom, our classification model. Now to actually run it, right? So first we have to, go through the patch embeddings, right? Then we're gonna make the CLS token. And we're just going to expand it to be the size of our actual, patches, right? So we just make it the same size as a patch. So we're just going to say x dot. So we're just going to find the shape of the first patch. Then, we're just going to duplicate whatever else, right? Then we're going to set the actual list of all patches to be Pytorch dot cat. We're concatenating these together, and so obviously we ensure that it maintains a dimensionality of 1. So we're not concatenating it like a pseudo 2D type thing. It's just putting it at start, and then we're going to start with the class token and end with the actual patch embeddings themselves. Right. And so then we're going to add the position embeddings to this. So x equals, I'm going to put this in a new line. X equals x plus self dot position embeddings, right? So this is just a variable, right? The neural network can just train this variable. And so obviously we're doing this differently to the original vision transformer paper, because those they just set as 0 to 15, but here we're just letting the model like train a number, right? And so then we're going to add dropout, right? X equals, we're going to do the dropout, right? Then, for every block, now we actually do the attention layers, right? So for every block in the blocks, x is equal to, right? So we're running the forward on all the blocks. Then we're just gonna do all the output stuff. So x is self dot norm of x, right? So we're gonna go through the normalization, and then we're just gonna say, hey, x is actually the first thing, right? We only care about the first thing. Basically, what the class token became, we're just going to take that, and then from there, what we're going to do is we're just going to do the final output step of it, what you could call unembedding, right? And then we're just going to, and so that's just going to be the logic for a predicted thing. And so there's the actual code for the model, right? So it's pretty simple. The attention is probably one of the most complex part, but other than that, that's just all the code you need for the model. And then now what we're going to do is we're going to go and create the training file. Now I'm going to get started on working on the actual training code, right? Like the training file. So I'm going to create the file. And so obviously there's nothing too interesting here. So what I'm going to end up doing is I'm just going to, because as you know, I've built this project before, and so I'm just going to bring code over and I'm just going to explain how it works, right? So I'm going to start by having the imports, right? So I'm just going to bring all the stuff in, and then, yeah, this is just all the stuff we have. We have just a bunch of standard libraries that help us with training, and then the vision transformer. Then I'm going to just set up all of the hyperparameters, right? So the hyperparameters we have here is we have batch size, epochs, learning rate, device, and the config. Then I'm going to do the dataset, but of course the dataset I need to show. The dataset we're going to be using is the CIFAR 10 dataset, and so as you can see, 32 by 32 color images, 32 by 32 by 3, as we've been seeing before, 10 classes, and 6,000 images per class. So there's 50,000 training and 10,000 test images, right? So just got a bunch of the images, and yeah. And so what I'm going to do now is, before you actually import the data, you always have to transform it into a form the LM can understand. Because if you actually use this directly, it'll be a NumPy array. And so in order to actually convert it, you have to convert it to a Pytorch tensor, and that's simple. That's just you just do some transforms, right? And so I've done a few more transforms here, right? So when we're actually running the training data set, randomly I'll just flip the image horizontally, right? So if we go over here, we can see, let's just use this picture of like a taxi. Sometimes it'll like 50% of the time, it'll be flipped horizontally, right? And so then this will basically just add some extra randomness to the training. And so in essence, you can kind of think of this as we have like double the data. Not really, but like you can kind of think of it like that. Compared to 10%, then we normalize it, right? And so these normalization values, they feel kind of random, but I pulled it from this GitHub comment of here's the correct normalization values, right? And so this basically makes training better because now all the data is normalized between, I believe it's normalized between 0 and 1, right? It might be between -1 and 1, but I believe it's between 0 and 1. Now we can actually like load the data set, right? So now we're actually going to load the data set. We're going to load it in with the like inside the data folder. So we're going to download the data. We'll load it in the data folder. We obviously have the training data set and the testing data set, right? And we're going to transform it to the given one. And when we're loading the train and test loader, we're going to load it. We have the Pytorch data loader. We'll load it to a certain batch size, and we're going to shuffle. And num work is based on your number of CPU cores. I'm gonna leave it to, you can set it to how many cores you have. I have an octa-core machine, but like it doesn't particularly matter because this is just like a one-time load, right? Next, I'm gonna actually have the model. So the model is our vision transformer and the config, and I'm just gonna move it to device. And so again, the device comes from up here, and the device is in essence CUDA, which is NVIDIA GPUs. If you have CUDA, otherwise you're just going to be using CPU, right? And so I believe you can have support for AMD cards and whatnot, but I use a CUDA GPU, and yeah, you can change it depending on what your actual hardware is, right? And so then, obviously, we're going to have the loss function, learning rate scheduler, and whatnot, right? And so we're just use cross entropy loss, Atom W optimizer, nothing too fancy here. Basically, we're going to set the learning rate to learning rate and the weight decay to 0.05. The reason we have a weight decay is so that, you know, stuff we've run previously will sometimes get forgotten, and so, yeah. And for learning scheduler, we're going to use cosine annealing, right, and the maximum is in epochs. This way we can, like, change the amount it's learning based on the actual, you know, time elapsed, right? So as we're going more on training data, we don't want it to, like, overcorrect, so we're going to slow the rate of learning, and there you go, there's a learning rate scheduler. Then I'm going to have a train step function, and so this is a little bit more complex. I'm going to just go through it a little bit more in depth, right? So first I'm going to call the train function on the actual model, right? And so this will just run through, this will just run through the actual model and run like a train step, right? This is just part of the Pytorch like module thing, right? And we'll keep track of like total loss corrected, like the total number we've gone through, right? And this so we can find out like how accurate the model is. And so we're just gonna use TQDM on our data loader, right? And we're basically just gonna enumerate through them. So we're gonna have the batch ID, right? So in any given epoch, we're gonna have a certain number of batches. So because with the data set we had 50,000 training images, what we're going to have is we're going to have 50,000 divided by 128 batches, right? Because our batch size is 128. So that's like 390-ish batches. So, and then we're going to iterate over that, and each of them is going to have the data in the target, right? And so first we're going to push them to our device, right? So we're just going to push them into, for me, in my case, it's GPU. If it's your CPU, we're just going to leave them there. Then we're going to like reset the optimizer to 0 grad, at least for this epoch. Then the output is basically, we're just going to run it through the model, right? So we're going to get the model to try to predict which class the images we fed into it are, and we're going to calculate the loss function from cross entropy loss, right? Based on what it actually outputted and the goal. Then we're going to do back propagation, and we're going to use the optimizer step forward, right? Then we're going to find the total loss, and we're just going to increment it by the loss, and then we're going to get the predicted total. And so again, we're just going to see how accurate it was, like correct over wrong, right? Like average loss is total loss over the length of the amount of stuff we're going through, like the length of the epoch, and then the accuracy is correct over the total, right? So we're going to find the accuracy over the epoch and the loss, right? And so we're going to return the loss and the accuracy. So this actually does the training, and this is just for like logs and whatnot. So because we're just going to run train, and it's going to run over an entire epoch. And then I have a very similar function for the testing set, right? And this basically, as you can see, does the exact same thing, but we don't actually do backpropagation. We just remove backpropagation. And there you go, right? We have it running on the testing set, and this just lets us test it so we know how it's like actually doing without introducing like overfitting or like effectively memorizing the answers, right? And then obviously we have the actual training loop, right? And so the actual training loop, what it is we keep track of the best accuracy the model's ever had. And so then for every epoch that we're doing, max epochs, we're going to have a training loss and training accuracy. So we're going to run a training step and a testing step, and we're going to have a step on the scheduler, right? So in the scheduler, it's going to adjust the learning rates and whatnot. And I'm going to print how well we did, right? So we're going to print we're on this epoch, we have this training loss and testing loss and whatnot. And if our tested accuracy is greater than best accuracy, so we have the new best model we've made, what we're going to do is we're going to save that as the best accuracy, and we're going to save the model itself to just a file, right? We're going to just dump the model to a file so that, the best model is there at the end. And we're going to print new best accuracy. Then, when it's done, we're going to just print training completed, best accuracy is this, and yeah. And so now, what we're able to do is, we're just able to like, just start a training run. And so, it's going to download the actual data, right? And then, you might be able to hear my fans start to spin up. And so now it's actually running the training. And so each epoch, because this is a relatively small data set, it's only going to take like 40-ish seconds, and we're only running 50. So this should take like 40 to 45 minutes to complete on my computer. On your computer, it could be a little bit slower. It might take like an hour or two. But I will come back to you when the training is done. Okay, so now the model has finished training. And that's when I'm going to leave the video off, but I'm just going to go through the results of the training, right? And so, obviously, after the first epoch, we went from roughly 10% accuracy, which is like, fully random model, to like 35% training accuracy, 43% testing accuracy, right? And so I think the model was just like doing some quick learnings. But then as it goes on and on, it slows down up until the very end, where we're at like 79% training accuracy and like 71% testing accuracy, right? And so obviously the best accuracy is roughly 71-ish, 71.2. And if you actually look in this folder, we see that we actually see the actual like model path saved. So later down the road, you can like actually pull this model in and maybe use it for some experiments or whatnot. And yeah, so I'm just going to summarize the video now. First, you understood a lot of the theory behind vision transformers. Then you, at least I'm assuming if you follow along, you built your own vision transformer and then trained it on the Sci-Fi 10 dataset or another dataset, and you just had to make some changes. And then now you have built a quick vision transformer that's able to classify sci-fi images, and now you can like scale up or whatnot. Like, I think some good next steps could be training a vision transformer to classify ImageNet, or potentially training a vision transformer to, say, tokenize images, or do something along those lines, right? And those are good next steps. And with that, I'm going to leave this video here. I wish you all a good day, and see ya.